Good morning to all of you. This is Rama Krishna from KL University, delivering series of lectures on heat transfer. And today's session is on transient heat conduction. That is one-dimensional unsteady state conduction. Particularly, we deal in this session the first case, that is lumped heat system or lumped heat parameter case. What the student will be able to understand at the end of this session. What is unsteady state conduction? What is the governing equation for one-dimensional unsteady state conduction? And what is a lumped parameter system? What is time constant? And what is the significance of Fourier number in heat transfer? And what is a semi-infinite body, and what is the importance of Slyer and Grover charts at the end of the part 2 and part 3 of unsteady state conduction. Now, transient heat conduction or unsteady state heat conduction means the temperature varies with respect to time. So far in the analysis we have done, always we assumed that the temperature at a particular point is constant and is not varying with respect to time. But in practice, if you take a hot body and leave it in the atmosphere, the temperature of the body gradually reduces. So as time varies, as time progresses, the temperature varies. That kind of variation which we notice with respect to temperature time is called unsteady state, also known as a transient. So transient means time dependent. And if we take one-dimensional conduction heat transfer in Cartesian system under unsteady state, the governing equation boils down to dou square T by dou x square, no y term, no z term, and no heat generation, equal to 1 by alpha dou capital T by dou small t, where T is the temperature which is varying with respect to x, and small t is the time, so which varies with respect to, which is accountable for variation of temperature with respect to time. So hence the solution of this equation is as a temperature as a function of x comma t in one-dimensional heat transfer problems. So if you look at this, if it is a simple equation like d square t by dx square, we can solve it. But it is now the temperature is a function of two variables, x and t, dou square t by dou x square equal to 1 by alpha dou t by dou small t. And now this equation, you need two boundary conditions and one initial condition. That one initial condition is at a time t equal to 0 seconds, what is the temperature of the body? So with reference to time initially, at time t equal to 0 seconds, what is the temperature? That condition we are specifying, hence it is called a initial condition. And with reference to x, it is a second order equation, you need two boundary conditions, and those two conditions are we are specifying with reference to a position in the body, and hence are known as boundary conditions. So to solve this one-dimensional unsteady state heat conduction equation without internal heat generation, we need two boundary conditions and one initial condition. A little bit complicated. So to solve this equation, different cases are proposed. The first case is lumped system analysis, or negligible internal resistance body, or Newtonian body, or infinite thermal conductivity system. And the second case is a semi-infinite body. And the third case is a general case. So these are three cases we will see in three parts. In addition to that, there are a few more cases where the convective transfer coefficient of the surroundings is infinite, like in the first case as we are assuming infinite thermal conductivity, or sinusoidal variation of the temperature. These are all different cases we assume to generate the boundary conditions. That is the purpose. So anyhow, let us go through the first case, lumped system analysis. To solve this equation, dou square T by dou x square equal to 1 by alpha dou T by dou T, the first approximation we made is we consider it as a lumped system. Now what is a lumped system? A lumped system is that a body having infinite thermal conductivity. When thermal conductivity is infinity, we know that there won't be any temperature gradient. So look at this figure. Suppose you consider a body like this. Let the temperature at the surface is T0. The thermal conductivity of this body is infinity, so which means there is no resistance for heat transfer and there won't be any temperature gradient, being K infinity dt by dx within this body becomes 0. So straight line. I mean horizontal line. With reference to T and X, if you plot a graph, it will be a horizontal line. So when the temperature at the surface is T0, at the center is also T0, somewhere here is also T0, somewhere here is also T0, here is also T0, or in other words, the entire body will be at a temperature T0, where T0 indicates a time T equal to 0 seconds. And T alpha is the surrounding temperature. So if you consider a body of infinite thermal conductivity, which indicates that it will be at same temperature. For example, say T0 is 300 degrees centigrade. You measure the temperature any point within the body, it will be 300 degrees centigrade. At the center also 300, at the surface also 300, somewhere at a point is also 300. Because we are assuming that the body thermal conductivity is infinity. When the conductivity is infinity, its resistance is negligible, and hence this case is also called negligible internal resistance system. Since this body is not offering any resistance for heat transfer, it is an ideal body and hence also known as Newtonian body. Since the entire body is at same temperature, it consists of heat energy as a lump and loses heat energy also as a lump, and hence this is also called lumped system analysis. For example, let the temperature of the body is 300 degrees centigrade initially. So throughout the body, any point you take, the temperature is 300 degrees centigrade. Imagine it is cooled now. So surface temperature drops from 300 to, imagine, to 200 degrees centigrade. Not only the surface temperature, at that point, all the temperatures, all the force within the body will reach a temperature of 200 degrees centigrade. So there won't be any temperature gradient at any point of time within the body, and hence it also loses heat as a lump and is known as lumped system analysis. I hope my point is clear. A body having infinite thermal conductivity or negligible internal resistance, or the body which maintains the same temperature throughout the body, is known as a lump system. By taking this assumption, indirectly you are making this temperature only a function of time. That is the secret involved in this. I am ruling out the temperature dependence on X because temperature at any point X remains same. So I am simplifying this problem by making the temperature independent of X and only depending on the time. So because it is a lumped body, the amount of heat it loses will reduce its heat capacity, and that will enter into the environment by means of convection. So the energy balance equation is heat lost by the body at any point of time is equal to the heat that enters into the environment by means of convection. So heat lost by the body, if this mass is m and imagine its specific heat is C and the temperature drop is say dT. Initial temperature T0, it may fall down to T. So it is mc dt by dt is the rate of heat lost by the body, because mc dt is only in joules. Only when you introduce the rate of heat loss, then it will become watts. Is heat loss to the environment by convection, which is equal to HA delta T, HA into T minus T alpha. The unit of this is watts and the unit of the other side also is in watts. Repeat, when mass of the body is m, its specific heat is C, the temperature drop is dT, heat loss is mcp dt or mc dt. But we need rate of heat loss. So per second, what is the loss? We will count mc dt by d small t. And this amount of heat loses into the environment by means of convection. Hence it is called HA T minus T alpha, where T is the temperature of the body at any point within the body after a time of small t seconds. Now dt by T minus T alpha is equal to minus HA d small t by mc. So dt by T minus T alpha is logarithm of T minus T alpha when you integrate, and mass is rho into V, density into volume, HA by rho VC dt. So this is equal to, minus sign is here, log T minus T alpha minus log T minus T alpha equal to minus HA by rho VC integral dt is T, plus we have to introduce a constant C1. Now to evaluate this constant C1, we apply the initial condition, that is at a time t equal to 0, the temperature T is equal to T0. At a time t equal to 0, the temperature time t equal to 0 seconds, we are assuming that the body temperature is T0. And at the time t equal to t seconds, let the temperature is T. That is what we have taken. Now by substituting this first initial condition, logarithm of T0 minus T alpha minus HA rho VC into 0 plus C1. So therefore the C1 value becomes logarithm of T0 minus T alpha. So therefore in the place of C1 we substitute log T naught minus T alpha. When this log T naught minus T alpha is taken to the left hand side, it is log T minus T alpha by T naught minus T alpha. So log T minus T alpha by T naught minus T alpha equal to minus HAT by rho VC, or T minus T alpha by T naught minus T alpha equal to e power minus HAT by rho VC, where T minus T alpha is designated as theta, T naught minus T alpha is temperature difference at the beginning, theta naught. So theta by theta naught equal to e power minus HAT by rho VC. This is the equation to determine the temperature within the body at any time t seconds. If you carefully observe this equation, there is no x parameter in this, which indicates that the temperature is made independent of x. Because the body is of infinite thermal conductivity, there won't be any temperature gradient. Whatever temperature is at the surface, the same temperature will be at the center, and the same temperature will be at all points within the body. So this is the first assumption: lumped heat system or Newtonian body or negligible internal resistance system or infinite thermal conductivity body. Now this HAT by rho VC, if you look at this term, you can convert this into H by multiplying with K both numerator and denominator, and multiplying with A both numerator and denominator, multiplying with V both numerator and denominator, you will get HV by Ka, Ka square by rho V square Ct. And we know the characteristic length LC is volume by surface area. So one volume by surface area becomes LC. So it becomes HLC by K, and this HLC by K is known as Biot number. It is the ratio of internal resistance offered to that of external resistance. And rho VC by K, K by rho VC is alpha, and again you have V by A, another V by A is LC square. So it becomes rho C by K alpha, V square by A square LC square, and T, alpha T by LC square, where alpha is thermal diffusivity, meter square per second, T is in second, LC square is meter square. So it is also a non-dimensional term known as Fourier number. So if you look at this equation, theta by theta naught equal to e power minus HAT by rho VC can be written as a Biot number and Fourier number. So in unsteady state discussion, the temperature variation with reference to time or position can be expressed in terms of a Biot number and Fourier number. And what is this Fourier number? Alpha T by LC square. Alpha represents thermal diffusivity. So the Fourier number is defined as rate of heat conduction in the body to that of rate heat storage in the same body. Alpha conductivity, rho C and L, it becomes something like heat capacity, heat storage. So Fourier number is the ratio of rate of heat conduction in the body to that of rate of heat storage within the body. It is alpha T by LC square. It represents the measure of rate of heat conduction when compared to that of heat storage in a given volume element. So you may get a question now. So if we assume a body has a lumped heat capacity system, temperature is becoming independent of x, and it is only evaluated with reference to the time. And the governing equation is theta by theta naught is e power minus HAT by rho VC, which can be in general expressed as a function of Biot number and Fourier number. So throughout unsteady state conduction, you involve two non-dimensional numbers. One is Biot number and other one is Fourier number. And what is this LC? The LC represents characteristic length, which is nothing but volume by surface area. For a sphere, LC is its volume by surface area R by 3. For a cube, LC is L by 6. And for a cylinder, neglecting the end surface area pi r squares, you will get cylinder LC is equal to R by T. Now, the moment you consider this negligible internal resistance system, as Biot number represents the ratio of internal resistance to external resistance, if we neglect the internal resistance, the Biot number value becomes very, very low. So therefore, lumped heat transfer case is applicable only when Biot number is less than or equal to 0.1, because again I will come back, Biot number is nothing but the ratio of internal resistance to external resistance. The internal resistance offered within the body for conduction heat transfer in a lumped heat capacity system, we are assuming it as negligibly small. Hence, the numerator is very low. Therefore, this system indicates the Biot number is less than 0.1. So, it is an approximation. When Biot number falls less than or equal to 0.1, you can consider that case as a lumped heat transfer case. Will practically this type of lumped heat transfer cases arise or not? Yes. For example, take a copper wire, electrical copper wire, maybe 20 gauge or 30 gauge. The diameter is very small, and when current is made to pass through, its temperature rises. So because of its thin, very small diameter, the temperature at the center and at any position, at any radius within that wire remains same, negligibly small. Conductivity of copper is very high, the diameter of the wire is very, very less. Therefore, there won't be any significant variation within the across the wire with reference to the radius R. So it can be treated as a lumped system, or where temperature is only depending on time, it does not depend on the radius or x direction. Similarly, take a hot steel bearing ball, spherical steel bearing ball, very small one. Steel thermal conductivity is very high. The diameter of that spherical ball is roughly 3 to 4 mm or 5 mm. So within that 5 mm, because of high thermal conductivity of steel, the variation of the temperature becomes negligibly small. So that case can be treated as lumped heat transfer case. So how to verify whether the case belongs to lumped heat transfer or not? That is, the check is with reference to its negligible internal resistance. The non-dimensional number involved with negligible internal resistance or internal resistance is Biot number. When internal resistance is negligibly small, the Biot number should be small. So therefore, to confirm whether a case belongs to lumped heat transfer or not, you have to first calculate the Biot number, and if Biot number is less than or equal to 0.1, you can treat that case as a lumped heat transfer case, and you can evaluate the temperature at any point with reference to time t by using the equation T minus T alpha by T naught minus T alpha is e power minus HAT by rho VC, where T is the temperature after a time of T seconds, T alpha surrounding fluid temperature, T naught initial temperature of the body at a time T equal to 0 seconds, H convective heat transfer coefficient of environment, A surface area of the body exposed to the environment, rho density of the body, V V is the volume of the body, and C is the specific heat of the body. Now, another important thing that arises in the lumped heat transfer analysis is, if you look at the equation T minus T alpha by e power minus HAT by rho VC, and if you make this HAT by rho VC equal to 1, That is, this HAT by rho VC will become 1 when T is equal to rho VC by HA. Follow carefully. I want to make this power, exponential power 1. That is possible only when I choose this T value equal to rho VC by HA. Now substitute in the place of T rho VC by HA, everything cancels and you will get 1. So this T equal to rho VC by HA is called time constant and is denoted by T star. So T star is rho VC by HA. The unit of rho VC by HA is seconds. So if T is equal to, carefully follow, if T is equal to 1 time star, that means if time T is equal to 1 rho VC by HA, then this power become e power minus 1. If T is equal to 2 times T star, what is T star value? Rho VC by HA. Now time I am substituting 2 times rho VC by HA. If I substitute T equal to 2 times rho VC by HA, then it becomes e power minus 2 and goes on like that. So a time constant is T star, the magnitude of which is equal to rho VC by HA. If you want one time constant, 1 rho VC by HA seconds, you have to substitute. If you are looking at 2 time constants, you have to keep the T value here 2 times rho VC by HA. A time constant T star magnitude is rho VC by HA and maybe 3 seconds or 4 seconds or 10 seconds or 1 hour. Nothing wrong in it. T star is not 1. Be careful. T star is rho VC by HA. For example, when I substitute rho VC HA in a given case, suppose I get T star equal to 3 seconds. Then I say the time constant is 3 seconds. 1 time constant means 3 seconds. 2 time constants means 2 into 3, 6 seconds. 3 time constants means 3 into 3, 9 seconds, like that. So 1 time constant is 1 rho VC by HA seconds. So if you make T equal to 1 time constant, 1 rho VC by HA, rho VC by HA, HA by rho VC cancels, you will get e power minus 1. If the time you have chosen is 2 time constants, then in the place of T, you have to substitute 2 T star. And what is T star? Rho VC by HA. 2 times rho VC by HA, this becomes e power minus 2. So how we define is, one time constant is defined as the time required for the temperature of the body to reach 63.2% of initial temperature difference, because e power minus 1 is 0.3678. So theta naught, theta is 36.78% of theta naught, or 100 minus 36.78, 63.2%. So it is the time required for the temperature of the body to reach 63.2% of its initial temperature difference. Look at this. We have defined one time constant like this. Time constant T star is rho VC by HA. And T minus T alpha by T naught minus T alpha equal to e power minus HA by rho VC into T. Now if you put T equal to 1 T star, then T minus T alpha by T naught minus T alpha will become e power minus 1. Am I clear? Similarly, if you put T equal to 3 T star, what is T star? Rho VC by HA. T T minus T alpha by T naught minus T alpha equal to e power minus HA by rho VC into 3T star. What is T star? HA by rho VC by HA cancels. You will get e power minus 3. For example, 3 T stars. HA by rho VC. In the place of T we keep 3 T stars, where T star is rho VC by HA. So HA 3 rho VC by HA. Rho VC by HA, HA by rho VC cancels, leaving with 3. So you will get e power minus 3. So this is e power minus 1, this is e power minus 2, this is e power minus 3, this is e power minus 4, and this is e power minus 5. So if you wait or if you choose time equal to 3 times stars, then T minus T alpha by T naught minus T alpha become 0.0497. If you choose the time T equal to 5 times T star, T minus T alpha by T naught minus T alpha will become 0.00673. What does it mean? Temperature of the body has reached 63.2% of its initial temperature difference. This T, body temperature, after one time constant will reach 63.2% of its initial temperature difference. If it is 3T star, the temperature of the body has reached 95.03% of its initial temperature difference. If it is 5 times T star, the body has reached 99.33% of initial temperature difference. That means still there exists an error in the estimation of temperature or in the temperature arrival 36.78% to that of environment. Still the body has not reached the temperature of the environment. There is a difference of 36.78% exists. In this 2 times T stars, 13.53% exists. 3 times T stars, 4.97 exists. In 5 times T stars, 0.67% exists. So this is the error. This concept of time constant is mostly used in assessment of temperature using thermocouples. When you use a thermocouple, the material of the thermocouple may be a combination of copper and constantan or nickel and copper, maybe anything, which we have a density rho, the volume of the thermocouple junction is V, its specific heat is C, exposed to a convective environment of H, and the surface area A. So let the time constant of that thermocouple T star rho VC by HA say 5 seconds. So that means the moment you keep the thermocouple in the fluid and take reading after one time constant, that means after 5 seconds, you will get an error of 36.78% because the temperature of the thermocouple has reached only 63.2% of its initial temperature difference, not yet reached 100%. So if you take the reading after 4 time constants, what is one time constant? Rho VC by HA. In our example, we have taken it as 5 seconds. That means after 20 seconds, if you take the reading, the temperature of the body has reached 98.17% of the initial temperature difference. Still, you encounter 1.83% error. If you wait for 5 T star, that is 5 time constants, that is 25 seconds, and take the reading, perhaps you may end up with only an error of 0.67%. So that is the meaning of the time constant. So when you are using thermocouple beads to measure the temperature, at least you have to wait for 4 to 5 time constants to give a good response to the thermocouple. Then the temperature recording will be with minimum error. And the time constant for a given thermocouple should be as low as possible. It could not be 1 hour. If it is 1 hour, you have to wait for minimum 5 time constant, means first reading you can take only after 5 hours. Should not be. As minimum as possible, say 1 second, imagine. Then after 5 seconds I can take the reading. Or 6 seconds I can take the reading. The error will be very less. So the response, it should be response changes in the surrounding environment temperature. That means the time constant of a thermocouple should be low. When, under what conditions the time constant of a thermocouple will be low? Only when its density is low, only when its specific heat is low. For example, copper is having low specific heat. That is why most of the thermocouple junctions are made up of copper and constant. And volume by surface area should be less, which means it should be in the shape of SPL. Thermocouple are to the extent possible made in shape. And it should exhibit high convective heat transfer coefficient with reference to the fluid medium. So you have to keep the thermocouple in an environment having high convective heat transfer coefficient, responds quickly to the change rate. So low density, low volume face area, low specific heat per coefficient are the characteristics of a good pull to have a low tense, so that its response time is also less. Response time generally varies from 5 to 5 or 6 time constants. So this is about the lumped heat capacity system. Now let us see some problems on it. Steel ball bearings of 1.2 centimeter dia are to be quenched in water in a heat treatment process. Balls are taken out from the furnace at 900 degrees centigrade and exposed to air at 30 degrees centigrade before they are dropped in water. What time the balls will take to reach 800 degrees centigrade in air with a convective transfer coefficient of 12.5 watts per meter square Kelvin. Hypothetical data, actually there won't be 900 degrees centigrade, 800, etc. But now the initial temperature of the ball is 900 degrees centigrade. And you are expecting the ball to reach 800 degrees centigrade at a time t equal to how many seconds? So density is 8000, H value 12.5, thermal conductivity to 15 watt per meter Kelvin, specific heat of the ball 480 joule per kg Kelvin, radius of the ball 0.6 into 10 power minus 2 meters, initial temperature 900, environment temperature 30, and 800 degrees centigrade is the time, the temperature at which it will arrive. Characteristic length of this ball is volume by surface area R by 3, that is 0.2 into 10 power minus 3 meters. Now whether this will fall in the lumped heat parameter system or not, or it is a Newtonian body or not, is the internal resistance considerable or negligible? So when you want to consider it as a negligible internal resistance system, you have to check number, ratio of internal resistance to external resistance, HLC by K. You will got 0.07 into 10 power minus 2, which indicates that it is a very, very low negligible internal resistance and is less than 0.1. Hence this case falls under the first category. So you can use the equation T minus T alpha by T naught minus T alpha equal to e power minus HAT by rho VC. H 12.5, V by A is R by 3, that is 0.6 by 3 into 10 power minus 2, density 800, specific heat 480 joules per kg Kelvin, and e power minus 800 minus 30 by 900 minus 30, you will get the time equal to 75 seconds. So after 75 seconds of leaving the balls in air at 30 degrees centigrade, they attain a temperature of 800. As this belongs to negligible internal resistance system, the surface temperature as well as surrounding temperature, temperature at the center and temperature at any position in the 1.2 centimeter diameter steel ball is one and the same. Let us have a look at second problem. A problem related to thermocouple, which is considered as 1 mm diameter sphere. The heat transfer coefficient is given as 500 watts per meter square Kelvin, and thermocouple thermal conductivity is 25 watt per meter Kelvin. Determine the time taken for thermocouple to record 99% of the temperature difference and find the time constant of thermocouple. Now let us calculate Biot number again. H LE by K. LC is R by 3 because it is sphere, which is less than 0.1, hence lumped system. 99% of temperature difference it has to record means the temperature difference between the source and thermocouple should be 1%. That is T minus T alpha by T naught minus T alpha equal to 1 by 100. Or in other words, this 1 by 100 is equal to e power minus H A T rho volume specific heat equal to etc., and you will get the time equal to 5.15 seconds. So the thermocouple will record 99% of the temperature difference after a time of 5.15 seconds. Now to find the time constant of thermocouple, T star equal to rho VEC by HA 1.12 seconds. You substitute this. This is what I said earlier. So for this particular thermocouple, the time constant is 1.12 seconds. So if you wait for 1.12 seconds and take the reading, it will reach only 63%. You have still 37% error. If you wait for 4 time constants and take the reading, it will reach around 98%. That is the table we have seen, this table. And you have 1.83% error. If you wait for 5 time constants, you will get an error of 0.67%. So that is, it indicates here, see, the time constant is 1.12 seconds. Roughly 5.15 seconds means it is roughly 5 time constants. After 5 time constants, it has recorded 99% of the temperature difference. Error is only 1%. You understand? So the time constant concept is very important to analyze, and the response time of the thermocouple, how much time it will take to respond as quickly as possible to the changes in the environment temperature. Now let us take another problem. A long cylindrical iron bar, maybe end faces are negligible, the areas of diameter 5 centimeters, initially at so and so, is exposed to a cold stream of air. Convective transfer coefficient is 80. Check whether lumped analysis is applicable or not. If it is suitable, determine the time required for the rod to reach 300 degrees centigrade. Let us see. Biot number H is given as 80 watt per meter square, and it is a cylinder R by 2, that is 2.5 by 2, 1.25 in 10 power minus 2 by K 60, less than 0.1. Hence T minus T alpha by T naught minus T alpha is e power minus HAT by rho VC. The temperature you are asked to reach 300 degrees centigrade. Initially it is at 700, environment is at 100. So T minus T alpha by T naught minus T alpha e power minus HAT by rho VC, that will give you T equal to 615.9 seconds or 10.2 minutes. So this is the third problem, one with reference to cylinder. So whenever the Boyd number falls less than 0.1, you can treat it as a lumped heat capacity system. Immediately you can apply the temperature distribution equation as a function of time alone, because now it doesn't depend on the position in the body, and you can analyze what time it will take to reach that particular temperature. So what are the things we have discussed now? The one-dimensional conduction equation under unsteady state is given by dou square T by dou x square equal to 1 by alpha dou T by dou small t. Systems having negligible internal resistance or infinite thermal conductivity, which is known as lumped system or Newtonian body. When Boyd number is less than 0.1, case can be approximated as a lumped heat capacity system. The importance is, in a lumped heat capacity system, temperature is only a function of time. It is independent of x, because the internal resistance is negligible. Throughout the body, the same temperature will be maintained altogether. And one time constant is defined as the time required for the temperature of the body to reach 63.2% of its initial temperature difference. And the time constant can be calculated by using the formula rho VC by HA. So, and time constant is denoted by T star. T star is equal to rho VC by HA. For any thermocouple junction, you can calculate the time constant using T star rho VC by HA. One time constant means required time to reach 63.2% of initial temperature difference. The time constant of a thermocouple should be as small as possible so that it responds quickly. In general, you have to wait for not less than 4 time constants to take the initial reading. Thank you.